Hi students, in the previous lecture we discussed about smoothing filter. Here we are going to discuss about sharpening filter in spatial domain. The name of that filter is Laplacian. So what do you mean by sharpening an image? The edges of an image will be more visible if we sharpen an image. And if you take the difference between the original image and the sharpened image, the edges will be available. So, we are making use of first order derivative and second order derivative. For that, we will explain with the help of an example. We have a simple image here. Here it is towards white. This is pure white. Here we have a dot. We are drawing a line through here. And this line passes through this dot, and the gray level value we come across in this line is plotted here. See this? This is almost white, so we start from here, and gradually the gray level value decreases and it is moving towards pure dark. So this is pure dark, so we will write over here this is dark and this is pure white. Then when it touches this dot, a sudden spike towards white, and then it comes down, then pure dark, then there is a line which passes through here. So when it reaches the line, there is a gradual up in the next pixel. If this is a pixel, the next pixel it is up, then it comes down again. When it reaches here, it's a edge of an object, we can say a sudden spike. So this gray level value is also plotted here. So we will take a larger image. So in signal processing we have discussed about all those functions. This can be called as a ramp function. This is a step function. Ramp means almost a constant slope line. So the gray level values are written over here in this array. So we have gray level values from 0 to 7 because it is represented using 3-bit. The gray level value is represented using 3-bit. So it is almost constant 5, then it comes down 4, 3, 2, 1 because it is constant slope. Difference between these two gray level values is 1. And constant here, then it is the next pixel, it is spike, then the next pixel it comes down, and so on. Now how to utilize first order derivative and second order derivative here. First derivative, if you have 2 pixels, how to take first derivative? See, if this is x and this is x plus 1, how to take the difference? Difference between two spatial coordinates. Here is x plus 1 and x. F of x plus 1 minus f of x. This is 3 and this is 2. What is f of x plus 1 minus f of x? It is 3 minus 2, that is 1. Now coming to second order derivative. When it comes to second order derivative, we have to consider one more pixel. So if this is x and this is x plus 1, we need to consider x minus 1 also. So how to take f of x plus 1 minus f of x? The first difference is difference between these 2 points. Now the second difference is the difference between, it is actually coming like, we will take the difference between these two. Okay, so f of x plus 1 minus f of x. Then the difference between these 2 points, that is f of x minus f of x minus 1. So second derivative is the difference between these two. So that is f of x plus 1, then minus plus f of x minus 1, then minus 2f of x. So this is second derivative. See this, f of x plus 1 plus f of x minus 2f of x. So now given a set of pixels and their grade level values, how to take first order derivative. So simply take the difference between these two. For example, if you want to get the first derivative of this point, this is our x and this is x plus 1. So f of x plus 1 minus f of x, that is minus 1. Now consider another example. This is our x plus 1 minus x, that is 7. So see this, at every point the gray level value is marked. Now coming to how to take second order derivative. So to take second order derivative of the point x, we need to consider these 2 points as well as x. So simply saying, take the difference between these two. So we will see one example, minus 1 minus 1, that is 0. Minus 1 minus 1, 0. Okay. So consider this point, minus 6, minus 6. So that is 12. So these two difference comes over here. Okay, minus 6, it is minus 12. Here it is minus 1, that is 0. Minus 1, 0. Maybe this point 5 minus 1 to 0. So minus 1. So this is how we take first order derivative and second derivative, and there are some properties for first order and second order derivatives that we will see, and it is to be noted every time. So see this point. Okay, we have ramp, we have isolated point, we have a constant slope. So first order derivative must be 0 in areas of constant intensity. See, first order derivative is 0 in constant area density. It is non-zero at the onset of an intensity step or ramp. It is non-zero. See, at the onset. Okay, see, it is at the start of a step function or a ramp. It is non-zero. Yes, it is non-zero. Then we have some more properties. It is non-zero along ramp. First order derivative is non-zero along ramp. Now coming to second order derivative, it must be 0 in constant areas. Yes, it is 0 in constant areas. It is 0 in constant areas. See this. Then it must be non-zero at the onset and end of an intensity step or ramp. It must be non-zero at the onset and end also. See, at the onset and end of a step or ramp. See, here it is ramp, onset and end. See, this is the end and this is the onset. Onset and end of a ramp, it is non-zero. See, it is non-zero at the onset and end. Here is the onset and the end of a ramp. So it is non-zero. And it is 0 along ramp. See, constant slope. So the difference gives us 0. So these are the properties of Now, how to utilize the second derivative for designing Laplacian filter? See, in this example, we can see along ramp function, the second derivative is 0. In constant area, it is 0. So, in constant area and slope, it is 0. But consider the case of this isolated point in a sudden spike. See, we have a spike value. From 6, it's a gradual up or down to minus 12. Here also, in the case of a step also, we have a sudden spike. See this here also. So, if we utilize the second order derivative, it is easy for us to find a spike, that is an edge. Only in edges we have a sudden spike. So, we are making utilize of the second order derivative result for finding sharpening filter that is based on Laplacian operator del square f, that is dou square f by dou x square plus dou square f by dou y square. So here we consider only x domain, dou square f by dou x square. We are going to consider dou square f by dou y square also. So we have two coordinates, x coordinate as well as y coordinate. So we are adding y2 in this derivation. So f of x plus 1y, f of x minus 1y minus 2 f of xy. The same second order derivative we saw earlier. Okay. Now dou square f by dou y square is with respect to y. So y plus 1, y minus 1 minus 2 f of xy. Now what is del square? The sum of these two. So f of x plus 1y, f of x minus 1y, then f of x y plus 1, then f of x y minus 1 minus 4 f of x y, not f, it is f of x y. So if you observe this, these values are very familiar for us. We call these 4 coordinates, the 4 neighbors of xy. So we have, if we have xy, this is our xy, these are the 4 neighbors. So what is the value over here? It is 1. It is 1. So write this 1 value in the 4 neighbors. Now what is in xy coordinate? It is minus 4. So write this minus 4 over here. So this is how we are going to design a filter. So in the other coordinate it is 0. So this is our Laplacian sharpening filter. This is the way of designing it. So see, this is the filter mask used to design a Laplacian filter. So if we consider in the other way, okay, just the reverse, then we have plus 4 over here and a minus 1 over this position. So this is also a Laplacian filter mask. Now we have an extension of the same if we consider our diagonal neighbors also. So we have 4 more values, then this becomes minus 8. Okay, this is the other way implementation. Now how to sharpen an image. Now how to sharpen an image? For that, Laplacian, apply Laplacian filter on an image. Okay, then that image is subtracted from the original image. So this is our Laplacian filtered image, and this is our original image. Depending on the center coefficient, if it is plus or minus, we have minus and plus over here. So we will see, here is an example. This is the image of the north pole of the moon. This is B is the Laplacian filtered image, and C is the Laplacian image scaled for display purpose. Okay, and it is image enhanced by the previous equation. So this is an example also. So that's all about sharpening filter. Thank you for listening.